In this video, we will work through how to calculate formal charge on atoms in a molecule. And I'm going to work through several examples that illustrates the process that's necessary to do this and how we can go about solving these types of problems. So first of all, let's define formal charge. Formal charge is an assignment of charge on atoms in a molecule specifically, and it assumes that chemical bonds are shared equally, which we know from electronegativity is not essentially true, because the electronegativity, certain atoms are going to want to hog those electrons more than other atoms in this sense. So it makes for an unequal sharing of the electrons in a chemical bond, and that is not something that is typically considered in formal charge. And we'll look at a few examples of where that can get into a little bit of a confusing situation, which is why it's called formal charge instead of just charge on the atom. So this is calculated, formal charge is calculated with the following formula. And bear with me, it's a little bit confusing, but we'll work through an example to make sense of it a little bit better. So first of all, formal charge, again, it's an assignment at a particular atom in a molecule. So you need to have a molecule to begin with. And again, as a review, an atom is just a particular element on the periodic table, whereas a molecule is a collection of those atoms that are structurally bound in a specific way to give you the molecule. So by definition, there has to be at least two atoms in a molecule, and an atom is simply just the element. So formal charge, its assignment on an atom. The first thing you have to identify is the number of valence electrons on a neutral atom for that particular element. So if you consider something like oxygen, you would look at your periodic table, you would see that it's in group 16, so the valence electrons would be 6 for a neutral oxygen. So that's what goes here in this first parentheses. Then you subtract the number of unshared electrons on that atom. So that would be lone pairs. If you have one lone pair, that would be 2 electrons that are unshared. If you had 2 lone pairs, that would be 4 electrons that are unshared. And that goes here. And then lastly, this is you subtract the number of bonds that are to that atom. So let's say you have one single bond to that atom, that counts as just 1 electron because of the assumption of formal charge that all chemical bonds share the electron density equally. So each bond we just assume is 1 electron at either atom for this formal charge counting. So now let's look at an example, and this will illustrate why we call it formal charge instead of just charge. So let's look at the hydronium ion as our example, keeping our formula in screen. So the H3O plus is the molecule that we're interested in. And if we first have to draw the structure for this molecule. So we have our oxygen as the center, and if we were to just draw something that looked like water, we would get this. But then again, we have a additional proton, additional hydrogen bound at the oxygen, so we get this molecule, and then we have a lone pair on the oxygen to give it an octet. And all those hydrogens are only in the first row, so they only can have access to the s orbitals and therefore only need 2 electrons to be have a full valence shell. Okay, so now let's go through this process here of calculating formal charge on each of these atoms. Let's start with the oxygen. So again, the first thing we need to do is look at the number of valence electrons on a neutral atom. So we'll go to our periodic table for this one. Here's oxygen, it's in group 16. Like I previously mentioned, we know that the oxygen then needs 6 electrons to be neutral in its neutral state. So we'll use that for our formal charge counting here. So if we say formal charge of the oxygen, I will put an O in parentheses for oxygen, and then this is now 6 electrons is what we want to be neutral. That's our first number. Then we subtract the number of unshared electrons, or in this case, our lone pairs. So here we have 1 lone pair, that's 2 electrons. And then we count each bond from the oxygen. So that is 3 single bonds, so that is 3 electrons. So this gives us 6 minus 2 is 4, minus 3 is 1, and it's positive. So this is a formal charge of positive 1 at the oxygen. we were to do the same process on hydrogen, I'm not going to explicitly draw it, I'll just talk through it. Hydrogen we know is in column 1, so let's look at the periodic table. Here's our hydrogen in group 1, so it has one valence electron to be neutral, so that would be like a 1 here, and then we count the number of valence, there's 0, so that's just 1 minus 0 is still 1, and then we subtract the number of bonds from the hydrogen, and each of these hydrogens are equivalent, they're bound just to the oxygen, so 1 minus 1, that's 0, so each of the hydrogens have a formal charge of 0, so we do not draw anything there. Like we don't have to draw a 0 to indicate 0 formal charge. Now, if you think about electronegativity, we know that oxygen is extremely more electronegative compared to the hydrogen. So if you think about actual electron density, you would imagine that there are dipole moments away from the hydrogens and towards the oxygen, right? Since the oxygen is more electronegative, it wants to hog that electron density more than the hydrogens, which in this case it does. So this is why it's called formal charge, is because the oxygen is simply taking count that we have a positive charge there for just the sake of an electron count. But we know that the electron density at the oxygens would be more, it would be more electron rich at the oxygen than at the hydrogens. And we know this because if we think about our acid-base chemistry, we know that this is a very strong acid and one of these protons could be removed. And if the protons are going to be removed, it would suggest that they are partially positive, which is true even though our formal charge would suggest that that doesn't make any sense, right? If we put a partial positive here, you would think now we have a positive charge and a partial positive. That doesn't really make sense, which is why, again, we call this a formal charge, and it has some limitations, but it's very useful as a tool to understand this. Okay, for the remainder of the video, we're going to work through several examples to illustrate this idea as best as I can. So, our question here, there's going to be 8 questions. I'll have timestamps in the video for each one, so feel free to click on whichever one is most relevant to you at this time. And all the questions are just going to be assign the formal charge, if any, on all the following molecules. So as we went through in our first example with the hydronium ion, the H3O+, if there is no formal charge at any of the atoms, you would simply put nothing. Just write that it is correct, and there's no need to put a formal charge. So with that, let's get right into it. So we're going to have to look at each atom in our molecule, and if you have a hydrogen-rich compound, like here it's not very hydrogen-rich, but there's hydrogen, I would do the hydrogen last, because it's more than likely that the hydrogen is not going to have a formal charge. So with that, let's start with the carbon then. So our carbon, we're going to start with the formal charge of carbon, so I'll write Fc in the parentheses with a C for a carbon, and we will have to look at our periodic table to see the number of valence electrons that carbon wants to be neutral. Carbon is in group 14, so that is 4 valence electrons for carbon to be neutral. So our first number here is 4 in our little equation. And then we subtract the number of valence electrons, or not the valence electrons, unshared electrons, which are lone pairs. And here the carbon has no lone pairs, so that is 0 for unshared. And then we subtract 1 for each of the bonds that are to that carbon. So here there's a carbon-nitrogen triple bond, so we count each of those bonds as 1, so that is 3. And then there's a carbon-hydrogen single bond that's not drawn, but that has to be there to fulfill the octet of the carbon. So that is 4 then, 1 for the carbon-hydrogen single bond, and then 3 for the carbon-nitrogen triple bond to give 4. And this is a formal charge then of 0. So the carbon gets nothing, and it is formal charge counting wise, it has a 0 charge. Now if we look at the nitrogen, formal charge of nitrogen, we'll look at our periodic table again, and to determine the number of valence electrons for nitrogen to be neutral. It's in group 15, so that is 5. So our first number here is 5. Then we subtract any lone pairs. Again, just like our carbon, this nitrogen has no lone pairs, so no unshared electrons, so that is 0. And then we subtract our number of bonds. We have a nitrogen-carbon triple bond, that's 3. Nitrogen-hydrogen single bond, that's 1. 3 plus 1 is 4, so we subtract 4 here. This is 5 minus 4 is positive 1. So our nitrogen gets a positive 1 charge, formal charge. If we look at each of the hydrogens, they are bound to just one atom. We know that hydrogen wants one electron to be neutral, so both of the hydrogens are neutral in this molecule, and we can move on to the next question. This is the only formal charge for this molecule. Okay, moving along. Here we have a protonated carbonyl. So in the functional group video, we talked about carbonyls have this carbon-oxygen double bond here. And this is such a carbonyl, but it has a additional proton at the oxygen involved in the carbonyl. And this will affect the formal charge. So let's start with the formal charge of the oxygen. So again, our formal charge of oxygen. How many electrons does oxygen need to be neutral? If we look at our periodic table, it is in group 16, so it needs 6. So 6 goes here. We subtract the number of unshared electrons, or lone pairs. Here there's one lone pair, that's 2 unshared electrons. Then we subtract all of our bonds. We have one oxygen-hydrogen bond, and then an oxygen-carbon double bond, so that's 2 plus 1 is 3. So this is 6 minus 5, which is positive 1. So again, our positive charge is going on our oxygen. But again, think about that. That suggests that the oxygen, which is much more electronegative than the hydrogen, has a positive charge and has less electron density. And we know that due to the electronegativity, it's unlikely that that is true. It's far more likely that that oxygen still has more electron density than the hydrogen or the carbon. So that's just something to keep in mind of the limitations of formal charge, but this is still useful for other uses. So now let's look at our carbon here. So our formal charge of the carbon. Again, we know carbon wants 4 to be neutral. We looked at that in the previous question. And it is doubly bound to the oxygen and single bound to another carbon and to another carbon. So that is 4. And there are no lone pairs, so we subtract the 0 unshared electrons, and then minus 4 for the bonds, that's 0. And then if we were to look at the other carbons that are on the periphery here, they all have 3 hydrogens to fulfill their octet. So the exact same equation would become true for those groups, which are called methyl groups, because they also have 4 bonds, 4 electrons in terms of the bonding. So that would give a formal charge of 0 as well. So the only charge here in this molecule is on the oxygen, positive charge. And again, I'm not sure if I went through this yet or not, but this hydrogen is bound to one atom. So again, lone pair, or the valence electrons for this hydrogen would be 1, minus the 1 bond for our formal charge counting is 0. So no charge at the hydrogen. Okay, here we have a BH4, boron bound to 4 hydrogen atoms. And again, let's start with the non-hydrogen atom, so the boron in this case. And let's look at our periodic table. This one is not ones that you may have memorized. You have to look at boron. Boron is in group 13, so that is 3 valence electrons to be neutral. So that is our first number here, is a 3. Subtract our lone pairs, there are none, so that is 0. Subtract 1 from each bond, there are 4 bonds, so we subtract 4, that is negative 1. Okay, so negative charge is on this boron. And then again, if you look at all the hydrogens, they're all bound to one atom, namely the boron. So they have no formal charge as well that we've looked at in previous questions, so there's no formal charge there. The only formal charge is on the boron. Now, this is an interesting molecule. You may be familiar with it as sodium borohydride. So this usually has a counter ion of a sodium metal, which is Na+, and this is a hydride source. So I think this is a good time to mention that a hydride is a hydrogen atom, but it differs in electron count. So a hydride is H-, so this is a hydrogen with a lone pair. Now, if you think about that lone pair, again, with our formal charge counting at this position, the hydrogen here, we know that hydrogen wants one electron to be neutral. Here it has a lone pair, so that is 2 electrons in our formal charge counting. It has no bonds now, so that's 0, so -1, hence the -1 charge on the hydrogen. And this is called a hydride when it has that negative charge. So sodium borohydride is a hydride source in which this bond here, any of the boron hydrogen bonds, are what is going to be functioning in the mechanism of whatever you're doing. This can reduce carbonyls. This is just an interesting molecule, and it's worthwhile to point out because here we have a hydride source versus a proton or a hydrogen, which are, again, hydrogen atoms, but they differ in electron count. All right, here we have another question. So again, let's begin with our non-hydrogen atoms. So let's just start with a carbon to be representative of all of these carbons here. So our formal charge of a carbon, again, we've already looked at our valence electron. It's in group 14, carbon is, so that is 4 to start with. And then we subtract our lone pairs. None of these carbons have lone pairs, right, as we do not see any, so there must be only bonds. So if that's the case, then they all must have 4 bonds, whether in double bonds or all single bonds. So that's 4 minus 4. All of the carbons are neutral. So, and if we want to be more explicit here, we can fill in the hydrogens. So there is a hydrogen at this carbon. So the carbon bound to a carbon, bound to a carbon, bound to a carbon. There's your 3 plus the hydrogen is 4. And this one has 2 hydrogens. This has 2 as well. And this has the additional hydrogen here, giving that the 4 bonds. This carbon has 2 hydrogens and 2 hydrogens. And then this one is a methyl group, so it has 3 hydrogens here. So now this illustrates more clearly that all of those carbons are bound to 4 other bonds, and hence that gives you the formal charge of 0. Now, pH, by the way, is phenyl. That's the abbreviation for phenyl, and phenyl is benzene. So benzene looks like this. So now again, if you look at all of those carbons rather, they have 4 bonds. 2 of them on each carbon is in the form of a double bond. So if we look at this one, that's carbon-carbon double bond, there's your 2 bonds. Then a carbon single bound to this carbon at the top, that's the 3rd bond, and then to that hydrogen lastly. So you can look at each one of those and convince yourself that they have 4 bonds, 2 of them in the double bond, and then 2 single bonds. Hence, all of those carbons would also have a formal charge of 0. So that's why when you see ppH3, this is the structure. It's a phosphorus bound to 3 benzenes. And this is why it is abbreviated, so we don't have to draw all of the benzene rings in there. But this would be that structure. And that phosphorus has a lone pair in the neutral form. But here it's bound, and that's where it gives its fourth bond. So to finish this question, then we have to look at the formal charge of the phosphorus, since we looked at all the carbons in the benzene and in the rest of the molecule. So our phosphorus this is a new atom in our questions here, so we need to look at our periodic table to see what is the formal charge that phosphorus, or the valence number that phosphorus wants. So phosphorus is in group 15, so the number of valence electrons is 5. So we start with 5. Count any lone pairs. In our molecule, the phosphorus has none. If it was in this state above, it would have a lone pair and hence 2 electrons. There are 2 here that would go here. And now if we look at this phosphorus, it's bound singly to 3 phenyl groups, 1, 2, 3, and then it's bound to the carbon in our cyclic structure. So that gives us 4 here. So this then, 5 minus 4 is positive 1. Hence, the positive charge goes on the phosphorus for our formal charge counting. If we were to look at this molecule and do the same thing, so our formal charge at this phosphorus, so let's call this P2 and call this one 2 here to distinguish them. You would have 5 again minus 2 minus 3 from the 3 bonds, 2 from the lone pair, and then 1 from each of the bonds to the benzene, so 3 total. So then this whole thing becomes 0. 5 minus 2 is 3, minus 3 is 0. Okay, here is the next question. So this is ozone, which is O3. So a lot of students incorrectly think this structure is actually this 3-membered ring, because if you look at this, this would have no formal charge at any of the oxygens. All of the oxygens would be neutral in terms of formal charge counting, but this is not the structure because this ring strain is far too demanding on this molecule for it to exist in this structure. So instead, it exists in this linear structure, which has multiple charges on the oxygens, which we'll answer here in this question. But the point is, this ring strain is far too demanding, because if we think about these oxygens, they all are going to have a bent shape, so they want this angle to be 104.5 if we go back to Vesper theory stuff. And this ring strain is making it such that those bond angles are 60 degrees. That is far too demanding on the molecules in each atom for it to exist in that way. So it simply doesn't, and exists in the charged state instead. So now let's look at each of these oxygens in terms of formal charge. They're all different, so I will label them 1, 2, and 3 to distinguish them. So our formal charge at oxygen number 1, if we look, we know oxygen has 6 valence electrons. If we look at our periodic table, as we've done a couple times now, then we subtract the number of valence number of lone pair electrons, which is 6 here. 3 lone pairs, 6 total electrons. 6 minus 6 is 0. And then we have to subtract the 1 bond between the oxygen 1 and oxygen 2. So this is 6 minus 7. This is negative 1. So our formal charge at oxygen number 1 is negative 1. Okay, now if we look at the formal charge of oxygen number 2, this again, valence, there's 6. We subtract the number of lone pairs. There are 2 electrons in the 1 lone pair. Then we subtract the 3 electrons involved in the bonds, right? The double bond is 2, the single bond is 1, so 1, 2, and 3, that's 3, and 2 minus 3 is 5, and then 6 minus 5 is positive 1. So here's our positive 1 on this oxygen number 2. And then if we look at the formal charge of oxygen number 3, again, the valence is 6. We subtract the lone pair electrons, there are 4. We subtract the bonds, there are 2 and just a 1 double bond, so 6 minus 6 is 0. Now, this is the answer, the negative charge on oxygen number 1 and positive charge on oxygen number 2. Now, if we look at the ring, they would all have this formal charge like oxygen number 3, because the valence for each oxygen is 6. There's 4 electrons in lone pairs, so that's minus 4, and then there's 2 bonds. So minus 2. So you would think that that's 0 at all of them. That's correct in terms of formal charge. But again, like I mentioned, it's the ring strain that dominates here, and this is not the structure. It is indeed the di-charged species that is the actual structure of ozone. Okay? And here is another example. So here we have nitrogen and oxygens that we have to look at. These oxygens are the same and different. So this is the identical to this one, and this one is different than both, and then we have our nitrogen. Now there is resonance involved here. We're not going to touch on that here in this video, but just so you know, all of these oxygens are really equivalent because the lone pair can resonate into this nitrogen and form a nitrogen-oxygen double bond, and then you can form a negative charge on the oxygen at the top, and you can make the same argument for this other oxygen. So in reality, they're all the same, but when you look at formal charge assessment, you look at the molecule in a snapshot, if you will, of this particular state, even though it can exist in a couple different resonance forms. This is how we treat formal charge. So let's look at our formal charge at oxygen number 1. Again, we said that the valence is 6 for oxygen. Each of these oxygen number 1 have 6 valence electrons, or 6 lone pair electrons, 3 three lone pairs for the 6 electrons. And then we subtract the 1 bond to the nitrogen. So 6 minus 6 minus 1, that's 6 minus 7, it's -1. So both oxygens labeled oxygen 1 have negative charges in their symmetry, so they're identical molecules. So you can convince yourself of that by doing the formal charge on both, but you'll see that they're both -1 for the reasons that I just mentioned. Now, if we look at oxygen number 2, this one's different. So again, valence is 6, minus the number of lone pair electrons, there are 4, minus the bonds, there are 2, the double bond to the oxygen here, and now that's 0. So oxygen number 2 has no charge in terms of formal charge counting. You'll hear me say that over and over in this video. It's just because I want to make it very clear that formal charge is just our way of keeping track of the electrons. It's not actually indicative of the electron density at particular atoms. Sometimes it is, but sometimes it's not, and it's just important to keep all of this together. Because the most common answer you can see in chemistry is just, it depends. There is no hard and fast rules. It's just sometimes things behave in this way and sometimes they don't, and it all depends on the context. So anyway, now we'll have to do this nitrogen. The formal charge of the nitrogen, valence is 5, as we looked at in a previous question. This nitrogen has no lone pairs. Oops, this is a minus. 5 minus, no lone pairs, so 0 unshared electrons. And then -4, because of the double bond, that's 2. And then the 2 single bonds to the oxygens, that gives you 4. 5 minus 4 is 1, +1. So this is a +1 on the nitrogen. So this molecule has a net charge of -1 because we have 2 counts of a -1 and 1 count of +1. So this gives us a overall net charge of -1 for this molecule. Okay, here is our last set of questions for this formal charge counting stuff. So again, let's start with our non-hydrogen atoms. So if we look at all of the carbons, we'll see that there's no formal charge. So you can look at the previous questions. I'm not going to explicitly do them here. I'll just show the hydrogens and then quickly go through why they would have a formal charge of 0. So again, we know carbon is in group 14, so it has 4 valence electrons when it's neutral. So if we look at this carbon, it's bound to this oxygen and another carbon, that's 2, and then 3, 4, the 2 hydrogens, that is 4 total. So it would be 4 minus 4, gives us 0 formal charge on that carbon. Identical for each one. You can convince yourself of that. Like I said, I'm not going to do it here since it was previously done in a different question. But now let's look at the formal charge of the oxygen. So again, oxygen is a valence of 6, and we subtract the number of unbonded or lone pair electrons, which is 2. And then we subtract the number of bonds, which there are 3 single bonds here. So again, this gives us a +1, 6 minus 5. So the oxygen has a formal charge of +1. But again, that oxygen is more electronegative than the hydrogen. So it is more likely that the electron density is felt more on the oxygen than on the hydrogen, which is why this proton is acidic and could be removed by a base. So don't fall into the trap of thinking that formal charge is the end-all be-all. There is always other factors in explaining the types of reactions that certain molecules undergo. So anyway, that's just a useful bit of information that will come up in other questions. So here we have a rather large molecule. This is our very last question. And we have to look at all the different oxygens because again, let's go through the carbons. All of the carbons would have no formal charge because again, they all have 4 bonds as I'm drawing in the hydrogens here. Right, and then if you consider this carbon, it has no hydrogen there because double bound to the oxygen and then single bound to this oxygen and then bound to the other carbon gives it a total then of 4 bonds, so therefore no charge on any of those. So, but these oxygens, some have charge, some do not. These are all not equivalent hydrogens. They're going to have the same charge, but they're different. There's no symmetry here, so I'm just going to label them all, and we'll go through each one. Okay, so we'll start with oxygen 1. Might as well go in order here. So formal charge, oxygen number 1 Again, valence is 6. We subtract the number of lone pair electrons. There are 6. We subtract the single bond here to that carbon. That is 1. So this oxygen at number 1 does have a negative charge. Again, this can resonate into oxygen 2, which if this was shown in a different form, it would, the other resonance form to be specific, you would have the negative charge on oxygen number 2 by our formal charge counting. But again, in formal charge, you just look at the single snapshot. So if we look at oxygen number 2, again, valence of 6, subtract the valence, there's lone pairs. There are 4 lone pair electrons. And then we subtract the bonds, which there is a double bond to that carbon, so that is 2. So 6 minus 4 minus 2 is 6 minus 6, which is 0. So there's no charge on the oxygen number 2. But again, with the resonance, you could put the no charge on oxygen number 1 and the charge on oxygen number 2, and you wouldn't really be able to distinguish them. So again, it's just, there is always this resonance possibility that you should be thinking about. Okay, now if we look at oxygen number 3, again, valence is 6. You subtract the number of lone pair electrons. There are 6. We subtract the single bond to that carbon, and that is negative 1. So there is a negative 1 formal charge on oxygen number 3. And then lastly, oxygen number 4. Again, the valence is 6. We subtract the number of valence or lone pairs, which is 4. The lone pair electrons, there are 4. And then we subtract the single bonds, which there are 2. 1 to this hydrogen, 1 to that carbon. So that's 6 minus 6, that is 0. So there's no formal charge on oxygen number 4. So that is the final molecule. So that is all I have for this video. I hope you found it useful. If you did, please leave a like and subscribe to the channel for more content like this. If you have any questions, feel free to leave them in the comment section below, and I'll answer it as quick as I can. And if you have any topic suggestions, please feel free to leave those in the comment section below as well. So I hope you all have a great day, and I'll see you in the next video.